First, welcome to Professor Peter Manstaro for the third talk of this series. I don't think we need to reintroduce again. Okay, let's welcome Peter. Thank you.
So this time I'll talk about the possible connections of cosmic rays and very high energy neutrinos in gamma ray bursts. And I think it's very probable that we'll get at least some contribution of these two types of messages from gamma ray bursts. The reason is that the standard model, or even the standard model with modifications, involves shocks. And if not shocks, it's magnetic reconnection. In either case, you're accelerating electrons. In order you're accelerating them to non-thermal relativistic energies, the electrons. And if you do that, then there must be protons around, and they must be accelerated too. And so cosmic rays may be accelerated in them, and then the photon densities are so high that you expect photohadronic interactions producing neutrinos. So the standard model shocks, or maybe the connection regions and external shocks, you can have acceleration in either one. In the photosphere, you can also have reconnection or shock and acceleration. Now, we have already indirect evidence for the acceleration of hadrons, I think, because hadrons resolve the radiative efficiency of the photospheres, and even if we stick to internal shock, they fix the radiative efficiency problem also of the internal shock. So either way, hadrons seem very useful. They seem essentially necessary, unless we have a completely magnetic model, sort of completely pulsar-like model, and I think that's unlikely. So given that, right? So we remember these are the different regions. So and then we have the dissipative photospheres. We can have the acceleration of the dissipative photospheres. And I mentioned that the dissipation can be caused by proton-neutron decoupling in elastic nuclear collisions, or magnetic reconnection. In both cases, we get proton acceleration. So I showed you the Bilogorodov model, okay, and that thing I showed too. And so in the modified internal shocks, right, so again going through the hadronic internal shocks do a good job. And so there seems to be indirect evidence in the form of photons. The photons from the hadronic secondaries appear to be present. So like the Fermi second component could be the inverse chemical radiation of the secondary components. Now we have done numerical calculations. In fact, Katsuaki Asano has an excellent computer code. So we've done a number of calculations of these hadronic secondary gamma rays. The time behaviors, it's actually a time-dependent Monte Carlo calculation. And then the neutrinos, you can calculate a neutrino light curve from a burst. So if the typical MEV photons have some light curve like that, and the GeV photons come delayed, they have a longer light curve, and the neutrinos last even longer. So these are P gamma secondaries, they take a certain time for the decay and all that. So there is one is predicting a neutrino signal that, could be, in terms of energetics, it's comparable to the photon signal. These just goes to show here that the purely leptonic model gives you a gamma ray spectrum, which is somewhat less prominent at high energies than the hadronic model. So the hadronic model with secondaries producing photons is better at producing these secondary components, so it's an added incentive for wanting to have these hadronic secondaries. Now, you ask yourself, okay, so let's take a typical GRB parameters, so moderate hadronic case. Is the photon spectrum. How do the neutrinos look like if you compare it to the ice cube limits? And so the typical GRB would appear to be below the ice cube limits. I mean, it is the diffuse flux from many GRBs. Okay? You could be having escaped neutrons that then might contribute to the cosmic ray flux seen by Auger. This is a preliminary calculation. I'll show you a more elaborate calculation of the same type, which is more interesting. So this is just a preliminary example. So the other calculation I mentioned before was the one with Kota-Murase et al. And there again, the photon secondaries were very important. Okay. So this calculation of, well, I'm just repeating what I said before, reacceleration of the secondaries produces a very nice photon spectrum, etc., etc. And so in the Murase et al. Calculation, we is the photon spectrum, and now here is the neutrino spectrum, mu squared phi d. So here's the neutrino diffuse flux for a hadronic model compared to the Waxman-Lacaille limit, or the Waxman-Lacaille limit with no evolution. So this is what the difference between a photospheric model, the neutrino spectrum of a photospheric model, it's way below the Waxman-Lacaille limit, or a classical Waxman-Lacaille internal shock model, which can get close to the Waxman-Lacaille limit and to the ice cube limit. And then what a typical hadronic model can do. Now, so if there are neutrinos, and of course there were protons being accelerated, fine, so that gives a nice gamma ray spectrum, and you might get some interesting neutrinos. Can they contribute to the very high energy cosmic ray flux that Auger is seeing, including the GZK cosmic rays of 10 to the 20 or so electron volts? Same argument as before. If electrons are accelerated, protons won't be accelerated, and then it's just a question of, do we get up to those energies? I'll argue that in some cases you can, and so GRBs may contribute to the GZK flux. So this is the diffuse cosmic ray flux, as observed by many observatories, and in particular with the Auger contributions, and in particular I was showing the GZK cutoff, and just emphasizing that these energies are much larger than the LHC energies obtained so far in the center of mass, by at least 3 orders of magnitude higher. So the cosmic ray spectrum, as you know, is enormously distended from 10 to the 9 to 10 to the 20 electron volts, 11 orders of magnitude in energy, but it's 31 orders of magnitude in intensity. The lower portion is observed by conventional balloons, up to maybe 10 to the 14, 10 to the 15. You can do it with satellites, with long duration, ultra long duration balloon flights. And further on, you need air shower arrays and underground detectors, and then medium air shower arrays, and then eventually you need very large arrays, which are of the order of thousands of kilometers squared. The spectral slope changes from an initial 2.65 to -3, and eventually it flattens again to something which is of the order of -2. And so this has been, simulated by a knee and an ankle. And so the question is, at the knee, is that where, that's where we think that supernova can accelerate protons up to about that energy, about 10 to the 15 electron volts. So that might be the limit of supernova proton acceleration. There is a second knee where, since the composition becomes more heavy, it may be that supernova can accelerate the heavy elements up to 10 to the 17 or so. There is a second knee which is not shown here. It's as if someone had a long knee. And so the clue is this composition, but at the ankle or here we definitely should be making a transition to extragalactic sources. So there are two clues. One is the anisotropies and the other is the energy cutoff. So minus 2.7, minus 3, and minus 2-ish again. There is mixed evidence here. So here the nuclear composition gets heavier and heavier. Here there is a lot of evidence for heavy nuclear, but then it's still in flux. So there is conflicting evidence, and there is some new input from the LHC, which seems to be changing the results on the X-max that indicates heavy elements. Now, as far as reaching the GZK energy, right, the Greisen-Kuzmin limit, how do we do it? That's a huge energy. It's about 16 joules or 4 calories. As you know, it's a microscopic energy. It's like 1/10 of the energy of a pistol bullet or a fast tennis ball. And so essentially it's where the CMB photons interacting with the protons cause the protons to decay. And then you get cosmic ray showers, and the cosmic ray showers have two components, an electromagnetic component and a hadronic component. And the hadronic component, the electromagnetic one, exhausts itself in the upper atmosphere. The muon component can reach the ground. Now, these very high energy cosmic rays cannot come from very far because of these GZK effect, the interaction with the CMB. The protons can at most have a mean free path of maybe 100 megaparsec or so. The heavier elements, they need to come from even closer. In fact, for heavy nuclei, it's photodissociation that is the main effect, not the photomeson interaction. But it just so happens that iron nuclei interact with the diffuse infrared background, and they have a somewhat similar mean free path. So there is a GZK radius which is of the order of 100 megaparsecs for both protons and ions. It's less for the intermediate elements. Now, Auger, as you know, is a mixed hybrid detector. On the one hand, it has surface detectors that detect the muons, so the Cherenkov light of muons in these water tanks. And then it has optical telescopes that look at the fluorescence light of the electron-positron pairs sort of hitting nitrogen molecules and producing fluorescence light, so it observes the fluorescence light. It's a huge array, 3,000 square kilometers, located in Argentina. Each one of these points is a water tank, and then there are 4 stations for the fluorescent detectors. Compared the area to New York City, it would encompass a very large chunk of most of New York City and the suburbs, so it's a big piece of real estate. And it's next to the Andes Mountains, a very nice location. 1,600 water tanks, as I mentioned, and 32 air fluorescence telescopes. The mountains also afford the possibility of looking at tau neutrinos from horizontal showers. So far, they haven't been detected. These are a little schematic of the size of the air fluorescence telescopes compared to a human being. These are the photomultiplier arrays. And let me just give you here a little movie which is about the Auger Observatory, which is made by some of the Italian members of the Auger collaboration. from Google Map. So the town of Malargüe is right next to it. It's actually a very small little provincial town, but it has these big influx of scientists which have completely changed their lives. They're used to seeing strange people come around them. So they work on the cosmic ray showers. And of course, the array has been completed now for 3 years or so, so it's been operating full time. And now they're starting on expansions. One is a low energy expansion going down to maybe 10 to the 17 electron volts, and one is trying to go to looking at lower latitudes. So here's a close-up of some of the individual elements. So these, one of the stations where you have the fluorescence detectors. And, they communicate with via radio to each other. And of course, the synchronization is done with satellite signals. These are the individual water tank locations. Fluorescence detector stations. Takes a little time, so maybe I have to accelerate. It's very romantic, but it's a lot of too much detail. Sorry?
One of the stereo events.
Yeah, one of the stereo events, right, that is being localized. So, move on. So the spectrum has been confirmed to have this definite cutoff. Now, it is compatible with what you expect from the GZK effect interaction with the CMB. Of course, there is a problem that if you calculate what is the maximum energy to which you can accelerate cosmic ray protons in any of the plausible sources, GRBs, AGNs, or hypernova, whatever, you also get the maximum energy around that value. So it's still unclear whether this is a maximum energy at the source or it's a maximum energy from propagation effects in the CMB. Well, at any rate, if it's this, if it's a CMB, it certainly comes at the right energy. So with all these high energy cosmic rays, can we use them to do astronomy? There was an interesting paper published about 2007, where Auger put out an apparent correlation of the 28 events of energies greater than 18.5 electron volts, 5.6 times 10 to the 19 electron volts, and nearby AGNs from the Veroncetti catalog. And so there was maybe some accumulation towards Centaurus A, the nearest weak AGN. It looked very nice. So all these seem to make a reasonable amount of sense. So the circles are the arrow circles if the cosmic rays are protons. Of course, if they were heavy nuclei, they would be larger arrow circles. But if you consider that they are protons, then you can see, how they correlate to the little stars, which are these AGNs. And then you find a signal, which is maybe 3 sigma. Okay? Was published in Science. It was very exciting. and that was great. But later observations, further observations, a couple of years later with more events, then reduced the significance of the signal. And so eventually it's below 2 sigma now. So one really cannot say that there is a correlation with these Veroncetti AGNs. It's maybe not surprising because these Veroncetti AGNs are very weak AGNs. Previously they were not thought to be the candidates for cosmic ray acceleration. It just so happened that, they took a catalog. This was the catalog that was the easiest to deal with, and then the easiest to do a correlation analysis, and it gave initially this signal, but the signal has disappeared. So maybe it's correlated, so it's not correlated to these objects. So could there be other type of objects? Could they be gamma ray bursts, or maybe hypernova, or maybe hydrogen stars, or maybe they originate in more common galaxies? Or if they're heavy nuclei, then they could correlate with anything because those aerocircles are much larger. Now, they could be heavy nuclei. If you look at the X max, the height above, from the Earth, the height from the top of the atmosphere to which the cosmic rays penetrate before they interact versus energy, or if you look at the variance of the RMS variation of the X max with energy, then you find that comparing it to Monte Carlo simulations of what you get from your Monte Carlo, it would seem that so this is what you expect for protons, this is what you expect for iron, and so it seems that as you go up in energy, the composition gets heavier and heavier, and also gets heavier and heavier. This was the status from 2010, 2011, 2012, and so it seems that there was these increase in the heaviness of the composition of high energies. There is new data from the LHC, as I understand now, that is causing the Monte Carlo codes, QGS jet, etc., to be recalibrated, and now maybe this signal is not so heavy as before. So the question is still open. If they had been heavy elements, then you know that if at high energies they correlated with the AGNs, then you know that the sort of the rigidity is what controls the acceleration, and so if you observe the nexus in spatial regions at high energies, and these are due to heavy nuclei, then you would have expected that protons at lower energies for the same rigidity would have shown the similar correlation. And so this kind of exercise was done, and one finds that one doesn't get an effect. You don't get the same correlation, and so either the high energy events are mainly protons, or else if they're heavy nuclei, then they're also heavy nuclei at low energies. So it must be said that, of course, at energies of 10 to the 16 and thereabouts, Cascade Grande and all that, they sort of show that there is a lot of heavy nuclei, but one would really have to sort of get a better handle on these compositions. It's all dependent on the simulation packages. Now, what about the maximal energy to which you can accelerate cosmic rays? You know the electric circuit analogy. So the gyro radius of a particle is the energy divided by the charge and the electric charge and the magnetic field. And so the gyro radius, the maximum energy, has to be one where the gyro radius is at most the size of the acceleration region. And so you can calculate for a circuit, some size R and magnetic field B, what is the potential, and so it gives you a maximum energy you can reach. It's proportional to E by R. And so that's a measure of, it's a Hillas criterion for your maximum energy. On the other hand, for the luminosity of the burst, it has to be larger than the magnetic luminosity that it would have. The magnetic luminosity is some surface area times the electromagnetic field density times the velocity of outflow, which is roughly c. And that, from here, you can express it as a function of these E proton max. And you have to add some relativistic correction factor for the fact that the expansion is relativistic. So you find that the luminosity of the object that accelerates cosmic rays to these energy has to be of the order of 10 to the 45 ergs per second times the Bork-Lorentz factor at which it expands. So the only objects then that have high enough Lorentz factors and high enough luminosities are GRBs or AGNs, or maybe in some cases so-called hypernovae or magnetars, which I will mention briefly a bit later. So, who could be these astrophysical candidates? As I say, for a long time, AGNs were thought to be the main candidates. In the last 15 years or so, GRBs have considered to be a very strong runner-up, if not a leading contender. And then maybe hypernova, a type of supernova with much higher ejection velocities and kinetic energies, or perhaps magnetars, pulsars with magnetic fields of 10 to the 14 or 10 to the 15 Gauss. Here is the same plot. Here is the Hillas plot showing the radius versus the magnetic field. And so it shows you that magnetars, AGNs, or hypernova candidates. Maybe accretion shocks on galaxy clusters is another possibility, but they get the right energies only if they're heavy elements that are being accelerated. So you need the composition to be heavy. Whereas AGNs and GRBs can accelerate to easy K energies, protons. Hypernova, again, they only accelerate into those energies if they're heavy elements. So the maximum energy, one can go through the calculations. So this is the Hillas criterion I mentioned before. This is the co-moving magnetic field, the co-moving size, and these multiplied by gamma to put it in the observer frame. And so, let's say if you have a shock radius, you know what the shock radius is. Let's say the external shock, and you can calculate in more detail what's the radius. Then you say that there is energy or competition of the magnetic field with the shock proton energy that gives you the magnetic field, and that gives you the radius, so you get your E max. And it's of the order of 2 times 10 to the 20 times Z. So for protons it's that, for heavy elements it could be larger, but it depends on the Bork-Lorentz factor and the external density, which determines the radius. For internal shocks, you can get a similar calculation, and you also get the number around 10 to the 20. So you all know how Fermi acceleration operates. You have, a shock, upstream fluid crossing, and then the particles scatter back and forth between upstream and downstreams. And since there is a difference in the bulk velocity, it's as if they're scattering between mirrors that are approaching to each other. So it's a converging flow. And then you calculate the probability of escape per cycle and the energy gain per cycle. And you compare that, so this is the escape probability as a function of the fluid parameters. And so you can eventually get that the spectrum you expect is something like e to the minus 2. It's related to the escape probability and the energy gain per cycle. And so the type of spectrum is okay. And now you ask yourself, is all the, so you need to get a diffuse flux. So you need to get the global energetics correctly. So there is a luminosity function of gamma ray bursts, which is expressed as some expression like that, meaning that that's the number of objects with a certain luminosity, some parallel of the luminosity. And you go through the numbers, etc., etc. And so you find that the input rate of energy from GRBs in gamma rays is of the order of 10 to the 43.5 Hertz per megaparsec cube per year. And the input rate in cosmic rays, protons, would be a comparable number